This tutorial will show you how to calculate the scattering curve from protein databank files, and how to use the fitting options in D+. First, in the domain view, we select the PDB file model, and then press the Add button. We select the file, in this case of lysozyme, and press Open. Notice we are at low level of details. At a higher level of details, you can see the atoms as spheres. Especially with large PDB files, it is important to keep low level of details. In our example, the center of mass of the lysozyme protein is not located at the origin. By checking on the Center PDB option when loading the PDB, we shift the center of mass of the structure to the origin. For single PDB files, this is the correct way of calculating the scattering curve. Off-center structures require a larger grid size, and as a consequence longer calculation time, to attain the same level of accuracy. We now delete the first off-centered PDB, and add a cylinder to approximate the size of the PDB structure, for a later use in the Suggest Parameters accessory tool. Here we open Suggest Parameters, and enter the enveloping cylinder dimensions to get the appropriate calculation parameters for our PDB model. We are now entering the suggested parameters into D+. Integration method of Monte Carlo, iterations of 1e to the 6th and so forth. Finally we click Generate. In the log intensity curve, you can see the scattering curve of lysozyme. We decrease a little bit the convergence field to produce a smoother curve, but the initial convergence of 0.001 is sufficient for most calculations. When we select the PDB in the objects tree, more options appear at the bottom, in the Parameters Editor pane. We changed the outer solvent electron density from 0 to 364. If 0 is selected, the solvation layer is not taken into account. We then select the Fill Holes option to add solvation in cavities in the structure that is sufficiently large to contain solvation layers. In the console window, which runs in the background whenever the GUI of D+ is open, we see the calculation time. Without including the solvation layer, the PDB calculation took less than a second. When the solvation was included, it took nearly 20 seconds. If we want to fit the solvation layer parameters, this may take many evaluations of similar length, and will take a long time. We shall now show a faster method for using the fitting option of D+ with a PDB file. We load an experimental signal of lysozyme, downloaded from the SASBDB database. We then click the Mutable option for both the domain scale and domain constant, and generate the initial curve. We ensure the appropriate fitting preferences are selected in the bottom right Fitting Preferences pane, based on the Suggest Parameters tool. When we see the resulting initial state curve, we click Fit to fit the mutable parameters, scale and background at this stage. The resulting fitted curve appears in blue as always. As you can see, it converged after 2 iterations, and it looks better. We now close D+ and reopen it to show a more elaborate fitting procedure. The experimental data that was loaded before is reloaded automatically. We add again the PDB, but this time we add 2 instances of the same PDB model. The first will be used for the solvent-subtracted scattering curve without a solvation layer, and the second will be used only for the solvation layer contribution. A manual symmetry model is added. Then the second PDB model is placed within the manual symmetry model, which has, in this case, only one layer. In the second PDB model we will only calculate the solvation layer contribution. As you can see, we clicked on the Solvent Only option in the parameter editor pane, and we set the outer solvent electron density to 1, and the solvent electron density to 0. The scale of the manual symmetry, which envelopes the solvation layer of the PDB structure, will essentially give us the electron density contrast between the solvation layer and the solvent. We used 4 as our initial guess, and used constraints for the fitting. The domain scale and the domain constant on the right pane are still mutable and will be fitted simultaneously. After the initial generation of the signal, we click Fit. We open the console and see the iterations flying by. The fitting is done, reached convergence after 2 iterations. This of course takes much more time when you fit the solvation layer thickness as well. The solvation layer scale that best fit the data was 3.98.